Today we're going to get into hooking our own systems into the low-level player loop. Now the reason I put Forbidden Unity in the thumbnail is because nobody ever talks about this for one thing, and Unity doesn't really document it for another, and it's not without some risks and gotchas, which we're going to talk about. What I want to do today is improve our timer system. Even though the timer class is pure C#, I still want it to be updated every frame the way that a mono behavior is. And we can do that by injecting our own system into the player loop. This can lead into all kinds of other improved systems such as data binding or input rebinding. So if that's what we're building today, let's get started. I thought I'd decompile the player loop class so that we can take a look at it quickly. Now this is in Unity's low-level namespace. There are three useful public methods here for us. The first one will get us the default player loop, which is an order of all the engine systems in Unity, the default order that is. The next one is to get the current player loop, which is the current state of it, which could have been modified and will be modified by us. And the last one here is set player loop. And this is when we've made some changes and we want to actually set the player loop to be the state that we want it to be in. I'm just going to jump to the bottom of this class so we can see a player loop system. A player loop system is represented by a struct, and you can see an example of one being created here in this class, but it's actually a graph-like system. You can see there's a subsystem list, which is an array of more player loop systems. So whenever we create a player loop system, think of it as a node in a graph. Those three public methods we were looking at expect to deal with the root of this whole structure. But what we want to do is be able to add our own C# classes as subsystems of the main player loop. So we're going to have to come up with a system here that will grab that loop, modify it, and then set it the way we want it to be. At the top of the system, we're going to have a bootstrapper class. The bootstrapper just needs one static method that'll be called initialize. I want this class to run as soon as all the assemblies have loaded, so I'm going to add the runtime initialize on load method attribute. Before I go any further, I'm going to also add using statements for UnityEngine.LowLevel and UnityEngine.PlayerLoop. So in the initialize method, the first thing we need to do is get the current state of the player loop. So let's use that public static method we were looking at earlier and get a reference to that. Now, before we start messing with it, I think it would be useful for us to actually look at what's inside this entire structure. So to do this, I've started a new file here, and I'm going to call this class PlayerLoopUtils. And so what we want to do is create a method that will recursively traverse this graph and output everything to the console. So let's create a new string builder here that we can pass down recursively. Might as well give it a title as well. Now, assume that we've passed in the root of the player loop system graph. Now we can iterate over every single subsystem in its subsystem list array. We'll make a little helper for that in a second. And when we get through that, we can just output the entire string builder to the console. So our little recursive helper needs to accept that subsystem as a parameter and also take in the string builder and the level that we're at in our recursion. Then we can just do a little indentation, and then we can add the system type into the string builder. If this is a leaf in the graph, then we've got nowhere else to go, and we can just return. Otherwise, let's iterate over every subsystem in this particular node, and again, we'll just recursively call that print subsystem method. Now that we've got our helper method written, we can come back into the main method and kick off the recursion inside of the for each loop here. With that done, let's jump back over to the bootstrapper and make sure that where I put that comment, we're actually calling this method. That's really all we have to do to be able to take a peek into the Unity player loop. Let's go have a look. So I've reloaded everything and then just need to click play here. And there we go. We've got some output in the console. So what I'm going to do, actually, it's a little easier to see this in the regular console. So I'm just going to stop the game and then I'm going to drag in the plain general console here. And you can see I've got a lot of output. You got the title there that I specified, Unity Player Loop, and then we start going through the different systems. You can see fixed update, pre-late update, and here's the one that I want. I want to hook right into the update so that my timers class is going to run every single frame. And you can see you've got lots of other choices there. There's post, late update, there's fixed update, there's all kinds of stuff. I'll let you guys explore this at your leisure. Let's get back to the business of creating our own player loop system that we can inject into here. The system I actually want to inject into the player loop is going to be called a timer manager, and that's going to manage all of our timers. So for now, I'm just going to have an abstract class to represent the timers, and it needs one method, which is to tick. I want it to tick every update, and the timer manager is going to facilitate that. To do that, it's going to need a list of all the timers in my game. We're going to need a way for timers to add and remove themselves. I'm going to call those methods register timer and deregister timer. And the most important part is we actually need some code that's going to run every update. I'm going to call this method update timers. Sure, most of you see where this is going already. Just iterate over every timer in the list and make them tick. And finally, I need a cleanup method too that we're going to put into effect a little later. And so I'm just going to have a method here that will clear out the list. This file is already starting to get a little bit long. So what I'm going to do is move timer manager into its own file. And I'm also going to move timer into its own file. Okay, now we have a system we can actually insert into the player loop. How are we going to do that? Well, first of all, we're going to have to wrap it up in a player loop system as its own small subsystem. Let's keep a reference to that right at the top of the class. Because we're going to have to actually define and then insert this system into the loop, I'm going to create some methods to kind of separate concerns a bit. I'm going to make this helper method generic because I want the T to represent which system in the player loop I want my system to be a subsystem of. In my case, it's going to be update, but you could make it a child really of any of the subsystems. As parameters, let's bring in a reference to the player loop and also an index of where in the subsystem we want to position this. So let's define our player loop system. We'll call it timer system. It needs to know the type, which is type of timer manager. It needs an update delegate. That's which method is going to get called inside of that class. And that's our update timers method. And we can just set subsystem list to be null. Now, this was fairly specific to the timer manager, but for the actual injection into the player loop, I think what I'm going to do is make a helper method in our utility class because we could use it for other systems in the future. It's not really specific to the timer system. I'll just add the signature here as a reference and we can jump over to the utility class. I think I'll put it up at the top here so that we don't have a lot of scrolling. I'll just push everything else down. So we're going to insert a system into the player loop with a public method here. This method is going to accept the loop. It's going to accept the system to insert and also that index number. Again, we're going to use a little bit of recursion to find where we want to actually insert this thing. So if we've passed in the root of our player loop system, we can just start checking. Is this the one that we want? Is this type T? If it's not, let's start going recursively through everything until we find it. Let's deal with the recursion first, and we'll come back to what happens when we've successfully found it. So our little recursive method here is going to be very similar to what we did with the print subsystem. We're going to basically just check to see if we're at a leaf. If there's no more subsystems to recurse, then let's just get out of here. Otherwise, let's go over every single subsystem that belongs to this particular node, and we're going to check them too. We can easily check them just by calling the insert system method again. If that failed, just continue to the next subsystem. If it was successful, we're going to return true. If we actually get to the end, then there is no type T, and we can just return false. Okay, so what if we did find a match? What are we going to do? Well, this is where we're actually going to inject it. Let's make a list that'll hold all of the subsystems of our type T. And we can check if the subsystem list is not null. If it's not null, then let's add all the elements from that list into the list that we just defined. Then we can insert our system at the index we chose into this new list. Now that we've inserted our system into this list, we've got a complete list in the right sequence that we want to be under this type T. Let's set that to be the subsystem list of type T, then we can come back. Well, believe it or not, that's actually the most complicated part of this entire video. So why don't we actually see this in action? Where I left a comment here in the timer bootstrapper. Instead, let's actually call the method we just wrote and insert our system into the player loop. Up in our initialize method, we can now call this helper method where T is going to be of type update. I want our system to become a subsystem of the update loop system. I'm going to wrap it in an if condition and say if it didn't work, that means it returned false. Let's have a warning out in the console that says that our timer system was not initialized. Now, something that's very important to remember is just because we modified this graph of player loop systems, we haven't actually set it to be the one that Unity's going to use. So let's do that as a final step here. We can leave the print statement because I want to show you all something in a second. So first things first, I need to hit play and it's going to reload my domain here quickly, but we'll be able to take a look at the log. And what we want to do is make sure that our timer system, our timer manager actually got injected into there. Let's have a look under update. Let's scroll down here and look. There it is right at index 0, the first subsystem under the update system. Perfect. That's exactly what I wanted. Now, you could have injected it under any system. It could have gone under fixed update or whatever you want. It really depends what kind of thing you're building. But for us, we want every frame for our timers to be ticking. Now, here's the first gotcha I want to show you. I had specifically turned on reload domain and scene for this, but normally I don't have that activated. What do you think will happen in this case? The domain didn't get reloaded. Let's take a quick look at our player loop output again. You're going to notice something very interesting. I'm sure quite a few of you are going to guess what has happened. And yes, we have two versions of the timer manager. Now, if this was a real scenario, that means I've got two managers that are exactly the same, and they are going to double the speed of all of my timers, which isn't good. Let's do a little bit of cleanup. So just like we had an insert system, let's have a remove system. Now, this really just has to walk the graph until it finds our system. We don't need to specify an index or anything. Again, we're just going to kind of do the inverse of the insert. So first, let's check if the subsystem list is null. If it is, we're done this level of recursion. We can return. Otherwise, let's get a copy of that list because we potentially are going to modify it. Let's iterate over everything and look for our system. And we can do that by matching type, which might be enough, but we can also check the update delegate that we assigned, which in our case was the update timers method. If we find our system, let's remove it, and then let's assign that list back as the subsystem list of this particular node. Now, potentially, we could have inserted it in more places, so we got to check all the children too. Let's make a helper here. We'll call it handle subsystem loop for removal. So let's define the signature really quick. And the first order of business in here is if the subsystem list is null, we can just bail out. Otherwise, let's iterate the entire subsystem list, and we can check each of them just by calling our remove system method again. Eventually, this method will go through the entire graph and remove any instances that we might have placed in there of our system. Now we can go back to the Bootstrapper and make sure that when we come out of play mode, we can clean everything up. Let's do that with a little hook into the play mode state changed event. So let's wrap that up in a preprocessor directive. And what we can do is, first of all, unsubscribe because I don't want to be subscribed more than one time. And then we'll just resubscribe ourselves with a little helper method. Now, this little helper is going to accept the state. The state can represent whether we're coming in and out of play mode and so on. There's several different kinds. But what we want is when we're exiting play mode, we're going to do our cleanup. We're going to get our current player loop, and we're going to create a helper, just like our insert timer manager of type T. We're going to do a remove timer manager of type T. I don't necessarily need the type T for this because, as you recall, we're recursing the entire list, but it might be a consideration for some systems in the future, something to think about anyway. So this is just a wrapper around our helper method that's going to pass in the loop that we provide as well as our timer system. For those of you unfamiliar with the in keyword, it means that we're passing something in by reference, but it is read only within the context of the method that it's being provided to. Now, back up where we're dealing with the play mode state change, let's actually call the remove timer manager. We'll pass in update as the type T. When that's done, we can again call the set player loop method. Now, one more gotcha in Unity is that Unity does not guarantee the clearing of statics. So let's make sure we call the timer manager's clear method. That'll make sure that our static list of all the timers gets cleared every time we exit play mode. Okay, I'm going to click play. And when I do, I expect to only see one instance of my timer manager there, no matter how many times I come in and out of play mode. Now, I expect to only see one version of the timer manager in here now. And yeah, sure enough, there is only one. Now, I've recompiled and run it a few times while I was recording this. It's all working as expected, and you'll see that too when we actually hook it up to these dials I've got on the screen. Because timer manager is a static class, if I register it as a subsystem multiple times, it's going to tick all the timers multiple times. So that's a real problem for this system, but it could be a real problem for other systems too, like suppose you're building a binding system that ties into all this. Okay, last piece of the puzzle is we need to implement the actual timer class. Now, this is going to be very similar to the timer class that we've been using forever on this channel, with just some small modifications to work with our new system. Let's walk through it really quickly and get this thing implemented. So a timer, of course, needs to know what its current time is and be able to provide that to the consumer. Likewise, a Boolean indicating whether the timer is running or not is useful. Let's keep a protected variable here with the initial time. Let's expose a public property that would show progress. We can clamp that between 0 and 1. Just like our old timer, let's also have events that will get fired when the timer starts and when the timer stops. And let's have a constructor that'll accept our initial time through as a parameter and set it. Then we're going to need some public methods to interact with the timer. The first one will be, of course, to start the timer running. Calling the start method will set the current time to the initial time again. And if the timer wasn't already running, then let's turn is running on to true. Now that our timer started, let's register it with the timer manager. And let's also fire off that onTimerStart event. And that's it for start, but we also need a stop method in case we want to ever stop the timer, and that's just basically going to do the inverse. So we can say if it is running, then we're going to do everything we need to do to stop it. Is running becomes false, we deregister from the timer manager, and we fire off that event. I'll just jump down to the bottom of the file again, give us some room. Implementers of the timer class are going to have to provide their own tick method, but I also want them to provide an isFinished property. That's because a countdown timer definitely has a finish point. When it reaches 0, it's done. But if you were making a stopwatch timer, it might count up forever. Okay, just a few more methods. Let's have a resume and a pause. That'll just toggle is running, really. So if we needed to pause a timer and then get back to it later, we could. I'm also going to want to be able to reset the timer. So that would be setting current time right back to the initial time, or we could have a reset method that accepts a new time. So we don't have to create a new timer if we just want to reuse an old one with a new time. Okay, we're almost done. I just want to do one more thing, and that is I want to implement the dispose pattern with this particular object. And that's because there could be some scenarios where a timer doesn't deregister itself from the timer manager, never gets garbage collected. So going forward with our timer class, let's just make sure that if we create a timer, when we're done using it, let's dispose of it too. To do this, we're going to implement the iDisposable interface, which has one method called dispose. But I'm also going to have a virtual method that will accept a Boolean true or false, are we disposing or not. And that's because I want to be able to call this from the finalizer, and I want implementers to be able to override it if they want. So the finalizer will call dispose with false. But our dispose method is going to call the virtual dispose method with a value of true and then suppress the finalizer. That's the same thing as telling the garbage collector that it doesn't need to call the finalizer because all the resources have been freed already. So let's fill out this virtual method. First, we'll have a private Boolean disposed because I don't want to run this virtual method more than once. If disposed has been set to true, we're going to bail out of this. Otherwise, if we are disposing, meaning we're coming here from the dispose method, let's make sure that our timer manager does not have a pointer to this timer anymore by deregistering, and then let's set that dispose value to be true. I'll just add a quick comment over the dispose method here and probably revisit this with some documentation at some point in the future, but not during this video. All right, well, I don't really like having destruction logic right at the top of the class, so I'm just going to come down to the bottom and paste it in there. There we go. Now, how about we make a concrete implementation of this class so that we can actually test it, and that's going to be our classic countdown timer. There's actually not much to do here because the abstract class has most of the logic. However, we do need a public constructor, and we have two abstract members we have to implement. The first one is tick. So what do we want to do on a tick? Well, if it is running and the current time is greater than 0, then we want to decrement the current time by time.delta time. If we're still running and the current time is less than equal to 0, stop the timer. Now for our isFinished property, we can just say that we are finished if the current time is less than equal to 0. And that's really it. So how about we set up a little demo where we connect up our timers to some visuals. I'm going to be using this awesome asset from the store that I bought quite a while ago, and I really like this one. It's so easy to use. I'll have a link to it in the description. So I've got a little mono behavior here where I've already set up some references to two of those radial progress bars. So let's have two countdown timers, timer and timer 2. I'm also going to make some fields here where I can define the duration for both of those. Let's come down a little bit and define our start method where we can actually create two new countdown timers. All we need to do is create a new timer and pass in its initial duration, and then we can start it right away. We'll do the same thing with timer 2. Now we don't have to call the tick method or anything in update, but we should dispose of them in our onDestroy method. And maybe just for interest's sake, let's add some debug messages to the events on both timers so that we get a little message in the log when a timer starts and when it stops. Now, I do actually need an update method, but not for the timers. I need it for my visuals to stay updated with each timer's progress. So let's implement an update method here where I'm just going to do a little bit of setup. These progress bars have a very straightforward API. I'm just going to define how many segments I want in a bar, how many segments I want to show, which is going to be based on the timer's progress. Then on the first timer, I'm going to set its segment count, and I'm also going to set how many segments are actually been removed from it. Now on the child, I'm going to make it simpler. I'm just going to have one segment, which means it's a continuous bar, and we'll set a percentage on that one. So that I'll just pass in the timer 2's progress. Now, I just have to press play because I've already connected up the references. So here we go. You can see that my 10-second one had 10 segments. It's just counting down every second. And the slightly faster timer at 8 seconds finished already. I stopped it a little early there because I just want to run it again and make sure that it was actually removing itself from the player loop and we don't have two of them registered in the player loop for some reason. And yes, of course, it's still working great. We're going to keep working with this timer system in the future because a lot of you have been asking questions about packaging, about assembly definitions. And I think building our own system like this, as a channel and something that we're going to use in many videos in the future, this is a perfect opportunity for us to start diving into those types of concepts and ideas. And maybe more importantly than that, I hope this video is giving you some insights into how you can actually hook into the player loop. Now, you might notice up on my screen there, I've got some text that says binding test. And that's because I actually, at the same time as I was building the code for this video, I built a small binding system too. And there's nothing that's beyond reach and nothing beyond your imagination. And just to show you, I'm just going to hook it up to the progress as well. So I've bound up the progress of the red bar to the text that's up in the right corner. And so you can see that it's just counting down. So this is a very simple bind system that right before every update, it just makes sure that one variable has the same value as another one. I'm sure you can imagine just from watching this video that it's not really a big stretch from what we did with the timers. That being said, it's more code than I want to get into during this video, but I'm sure we'll be talking about it more and these kinds of ideas in the future. So that's all I've got for you today. Thanks for watching. Click the like button if you haven't. Subscribe if you want to watch more. And I'll put a few video links up on the screen. Maybe I'll see you there.